Hello everyone, my name is Afsuna Afzal and today I'm presenting SOSRepair, Expressive Semantic Search for Real-World Program Repair. This is a work that I've done with my colleagues Manish Mutwani, Katie Stoley, Yuri Barun, and Claire Ligues. This is a collaboration between Carnegie Mellon University, North Carolina State University, and University of Massachusetts Amherst. Automated program repair techniques attempt to automatically produce patches for software defects. There are tons, maybe even hundreds, of different automated program repair techniques out there, but in general, they take a buggy program and a set of passing and failing test cases, and they attempt to find a patch that allows the program to pass all the test cases. One of the problems with these approaches are the quality of the patches that they create. Since these techniques rely on the test cases to find fixes, they can overfit to a particular test suite, which means that they can generate patches that pass all the test cases, but they don't fix the underlying problem. Let me give you an example. Here we have a very simple program that tries to find the maximum of two numbers, A and B. It passes two of its test cases, but fails on cases where A and B are equal. Now, we have the recur technique that attempts to find a fix for this program. It can tweak the program until all the tests pass. For example, it can create this patch. Even though this patch passes all the test cases, it does not fix the underlying problem, which is the miscalculation of the maximum of two equal numbers. We can recognize this overfitting problem by running a secondary set of test cases that are kept from the repair technique and observe that the patch fails a test in this secondary test suite. So now that we know about the overfitting problem, how can we try to overcome it and create higher quality patches? Earlier work shows that higher granularity semantic-based changes can actually improve quality. It means that since human written code is highly redundant, we can search for semantically similar code snippets taken from other places in the code base or other code repositories to replace the code at a higher granularity. For example, here we can look for a code snippet that also finds the maximum of two numbers, and we can try to use that to generate a patch at a higher granularity. This idea has been explored for small programs and showed a lot of promise for generating high quality patches. However, it has never been applied to real and large programs since it does not scale. So that's why we created SOSRepair. SOSRepair is the first semantic search-based automated program repair approach that actually scales to large real-world programs. To just give you an idea, SOSRepair scales to programs with more than 2 million lines of code, whereas the earlier approach only scaled to programs with maximum 25 lines of code. To allow SOSRepair to scale to real-world programs, we had to rethink everything about this search approach and come up with innovations that allows the approach to scale. Here are some of the key innovations. We developed a novel, more efficient and more scalable semantic search query encoding, and we extended the state-of-the-art constraint encoding mechanism to handle real-world C language constructs and behaviors. In addition to that, we extended the search technique to encode deletion and insertion. And these are just some of the key innovations in SOSRepair. Let me tell you about a real-world bug in the Python interpreter, which is a real-world system with more than 400,000 lines of code that SOSRepair is targeting. This bug caused the Python interpreter to misbehave on cases where a negative timeout is passed to the function. And here is a fix that the developers created for this bug. Something interesting about this bug is that if we look at other locations in the same code base, we will find this snippet of code, which is very similar to what the developers wrote to fix the problem here, except for the variable names and the error message. So SOSRepair uses this snippet of code to create this patch, which is identical to what the developers created except for the error message. Before I dive deeper into how SOSRepair works, I want to give you an idea how it actually performs on real programs. So we evaluated SOSRepair on ManyBugs benchmark, which consists of defects in large real-world C programs. And to measure the quality of the patches that SOSRepair creates, we created secondary or held-out test cases for the defects that it can patch. Overall, SOSRepair created patches for 22 of the 65 real-world defects in this benchmark that falls within its defect class, and 9 of these patches pass 100% of the held-out test cases. We also compared to other approaches, and let's take a look at this table. So here we are comparing SOSRepair to GenProg. GenProg and SOSRepair patch 16 of the same defects, and from these 16 patches that they create, SOSRepair create 8 patches that pass all the secondary test cases, whereas GenProg creates only 4 patches that pass all secondary test cases. And overall, you can see the mean quality of the patches that SOSRepair creates are significantly higher than GenProg. We also compared to more recent approaches, Prophet and Angelix, and we show that the quality of the patches that SOSRepair creates are slightly better than the other approaches, and the number of patches that pass 100% of the held-out test cases are similar to these other approaches. So overall, we show that semantic search-based approach to generating patches, to automatically generating patches has a lot of promise. So now let me give you an overview of our approach. So here I'm going to give you a high-level description of how SOSRepair works. First of all, we need to create a database of code snippets and their semantic encoding. This is a price that we have to pay only once for many of the defects, many of the repairs we are trying to generate. The next, for a given program and a set of test cases, we have to create an encoding that describes what the buggy code intended to do. Now that we have these two pieces, we will take a snippet of code from our database, and we take the encoding of the buggy code, and we create a query that asks, can this snippet of code be used to fix the bug? We pass this query to an SMT solver, such as Z3, and if the SMT solver finds this query satisfiable, we will create a patch and check whether the test cases, all the test cases pass. In that case, we have found a patch, a viable patch, and if they do not, then we go back to the step of getting another snippet of code from our database. So this is a very high-level description of how SOSRepair works, but in more details, SOSRepair looks like this. So I am going to walk you through these steps one by one. So I will first start with this step, which is the candidate snippet encoding. The goal of this step is to create a database of code snippets. For this purpose, we take a code repository, which can include code from the same code base as the program that we are trying to fix, and we split the code into snippets of desired length, let's say 3 to 7 lines of code. Then we use symbolic execution to capture the semantics behind these snippets of code. Let me give you an example. So we have this piece of code that is finding the maximum of two numbers. First, we find the inputs and outputs to this snippet of code. Then we pass these to a symbolic execution engine, and what it returns looks something like this. So these constraints describe the semantics behind what this piece of code is doing. And then we store this information in our database. There are some scalability concerns at this step. So for example, if you are handling only small programs, you only need to handle primitive types like integers, float, characters. But since SOSRepair wants to handle real-world programs, it has to handle real-world C language constructs, such as structs, pointers, multiple output variable assignments, console output, loops, and library calls. In the paper, we go into more details of how we actually handle these real-world C language constructs. So now that I talked about the code snippet generation, I am going to talk about the profile construction. So in this step, we want to capture what the buggy program is supposed to do. We first need to find the faulty line or lines using automated fault localization. And then we use test cases to create a profile of inputs and outputs to this buggy snippet of code. Back to our example, let's assume using automated fault localization, we identified this buggy snippet of code. Then we need to create constraints based on the test cases that describe the expected behavior of this piece of code. So these constraints, that we call them profile, look something like this. So for the first test case, we specify that if A is 3 and B is 2, then largest should be 3. And similarly, for the second test case, we say if A is 1 and B is 5, largest should be 5. And for the third test case, that is a failing test case, we specify that if A is 6 and B is 6, largest should not be 0. Now that we have our profile, I want to talk to you about how we create a query and how we pass it to an SMT solver. So we first select a snippet of code from our database that matches the input-output types that we are looking for. And then we use the profile and the snippet constraints to create a query that can tell us whether the snippet of code can be used to patch the program. So here's an example of the query. So I already showed you how we create the snippet constraints and how we create the profile. There is one problem here. The first set of constraints are using variables num1, num2, and max. And the second set of constraints are using variables a, b, and largest. And these two sets of constraints are not connected to each other in any way. So we need another piece for our query that can identify a valid mapping between two sets of variables. So here we have a, b, and largest on one side, and num1, num2, and max on the other side. One option is to try all possible combinations. So we'd first try this one, then try this combination, and so on and so forth. Obviously, this approach does not scale to large number of variables, which is pretty common in real-world programs. So this is one of the key innovations that allows SOSRepair to scale to large programs. We developed a novel, efficient encoding that finds a valid mapping between these two sets of variables in a single query. This approach was inspired by input-output component-based program synthesis, and I do not have time to go through how this approach works, and we go into details of how this encoding works in a single query, and I highly recommend taking a look at the paper to understand how it works. So now our query is complete. We have snippet constraints, we have the profile, and we have the mapping constraints. So now we can pass this query to the SMT solver. If the SMT solver finds this query unsatisfiable, we know that we cannot use the snippet of code to patch the program, and the snippet of code does not match the profile of the buggy program. On the other hand, if it tells us that it's satisfying, it will also tell us a valid mapping between two sets of variables, in which case we will move on to the next step, which is patch generation and iteration. So given a code snippet and a valid mapping, we have to create a patch and then run the test cases to see if the patch that we created actually passes all the test cases. So back to our example, we have the code snippet, we have a valid mapping, and we use that to create the patch that we were looking for and check whether it passes all the test cases. So again, here is just a very high-level idea of how SOSRepair works. There are many key innovations that we describe in the paper. In this presentation, I touched on the first two innovations, which is a more scalable semantic search query encoding and expressive encoding that captures real-world program behavior. I didn't have time to go through other innovations like searching for patches that insert or delete code, and how we automatically and iteratively refine the search query to encode negative behavior. But overall, we in this paper show that semantic search is a promising approach for producing high quality real world defect repairs. I already showed you this slide and talked to you about how SOSRepair performs on ManyBugs benchmark and how we compared it to other approaches. Another interesting finding that we present in this paper is the impact of fault localization on the patch quality. So in an experiment, we manually provided the fault location to SOSRepair, and by fault location, I mean the location that developers used to fix the program. And we observed that SOSRepair was able to find patches for 7 of the defects that it couldn't patch before. And 6 of these patches that it finds actually have very, very high quality. So they pass all the secondary test cases. And overall, we found that if we manually provide the fault location, SOSRepair would be able to create 23 patches, and 16 of them, so more than half of them, have very high quality and pass all secondary test cases. This suggests that progress in automated fault localization, which is an orthogonal problem to automated program repair, can actually have a significant impact on patch quality, and suggests that semi-automated approaches in which developers, for example, suggest fixed locations may actually result in producing high-quality patches. So there is more to the paper. There are many more experiments that we conducted to show the effectiveness of our innovations. I didn't have time to go through them, but I highly recommend reading the paper to get an idea of how the innovations we implemented in SOSRepair actually perform. We released the source code to our approach, and we also released a replication package for our experiments, which includes Docker containers that allow you to easily replicate the experiments. And we also release all the secondary held out test cases that we generated for the ManyBugs benchmark and used in our evaluation. To summarize, I talked to you about the overfitting problem in automated program repair approaches. I talked to you about how we can use semantic search-based approach to generate higher quality, high granularity patches, and how SOSRepair actually performs on real-world defects. Thank you for listening. If you have any questions, I would be happy to take them through any platform on Twitter or through email. Thank you very much.